All right, thank you very much for having me. And so I'm Bartosz. I'm a freelance ML engineer. I have a background in science, but now I'm working like a consultant for companies. And I will be talking about polars, but my message maybe is more general. I will try to convince you that you can use kind of database-like solutions to structure your applications, even if you don't have to connect to any database to get your data from. So I've been working in manufacturing recently, not really in car industry, but I mean, there's some similarities. When you look at the production line, you have many sensors, you have robots, so you have to integrate the data and control of this stuff in real time. So that seems to be a very good fit for this kind of environment because of its reliability, of course, performance when we talk about real time, and portability when we talk about both kind of workstations and also embedded devices. So unfortunately, Rust is not very much used now in the manufacturing. There is automation engineers are more used to kind of classical languages like ladder logic or maybe some simple Fortran-like textual languages. But kind of Rust is getting also some momentum, especially for edge computing and so-called digital twins. A bit more about it later. And so Polars is a library implemented in Rust, which implements data frames. Data frames are known from R very well. It's a kind of tabular data structure similar to spreadsheets, where you can basically start collect data for heterogeneous data, and then you can analyze it easily. It's used for so-called OLAP workloads, so online analytical processing, where basically you kind of run some analytical queries to analyze your data to get some business insight. And Polars has a very good APIs both in Rust and also in Python, and I will show you mainly examples, of course, in Rust. And the problem I'm going to talk about is kind of made up problem, but it has some similarities to what I've been working on. So this is a problem in which we try to process some manufactured units, for example, car parts, in real time, or even faster if you want to do some modeling or simulations. And then you screen them for quality and sort for downstream processing. So why would you like to do that? You might use it to adapt production parameters in real time to improve production yield, for example. You could also optimize warehouse capacity if you know how many units you can still store in the warehouse. Also, you could estimate delivery time for your clients. And the thing which I will be most interested in is to model the manufacturing process to have so-called digital twin, so that you can run the simulations offline outside the production and see what are the impacts of different changes that you can bring to the production and see how this affects your yields. And so this is the basic kind of program structure. Again, this is a made-up example. It's very much simplified. So, but the idea is very similar to what you might see in reality. You first define some control parameters. Then you use these parameters to set up your line and to produce a batch of units, in this case, a batch of car reflectors. And then you analyze these units to measure some quality statistics, such as number of faulty units and so on. And from this, you can then adapt the parameters of your production to improve the quality or maybe degrade it if the quality is too good. So depends what you really want to do. And I will all of these steps could be implemented in Rust with the same approach I'm going to present, but I will focus mainly on this control quality function. So the basic implementation of this function could look like as following. You have a function which takes a slice of car reflectors, and then it produces the quality statistics. So to calculate the statistics, you basically iterate over the reflectors. You take some attributes, and defect density and area, you multiply them together and sum them up in an accumulator. And at the end, you divide this sum by the number of reflectors to get the mean defect count. This is one way of implementing that in Rust using for loops. You could also use for the same, you could use also iterators or vectorization, and also this kind of OLAP-like solutions like polars. So let me show you how to implement it using iterators. So here you take again iterator over reflectors. You map them. You map each reflector to the product of defect density and area, and you sum it up. And then you divide it by the number of reflectors. So the advantage of this approach is kind of very simple. It's just a one-liner, and it also can be parallelized using, for example, rayon. Another approach is to use array libraries such as MD-array, where you construct the arrays from the attributes of the reflectors first, and then you multiply them, the arrays element-wise, using just the product operator, and then you average that together. So that's kind of very intuitive, especially for people who are used to this kind of numerical approaches. Can be also vectorized to use to SIMD instructions, and but it works mainly with the numerical types, integers or floats. So what I'm proposing is to use polars and data framing polars. So that data frame again is kind of tabular structure where you can have columns like colors, defect densities, and area. Each of the row in the column represents one reflector, and then all that you have to do. Also, there's some code missing here, but you want to take the column defect density and then multiply it by the column area. This is the area is missing here. I think it's hidden. And then after you select that, you calculate the average of this product. So it's similar to this SQL statement here, and the syntax is very similar in fact. And this is very expressive. It works also with heterogeneous data such as strings or date times or numbers. It's rather verbose here, but I don't find it very difficult to read. And the big advantage is that you have types which are only checked on runtime. So for example, when one of the columns is missing from the data frame here, you will not know until you run the code. So another advantage is that you have to convert your collections of reflectors to the data frame. To do that, first you have to construct a schema with the data types and names of the columns. Then you need to construct the rows for each of the item in the reflectors, and then you construct at the end data frame from rows. So this is kind of very verbose, but also another problem is that Polar's data frame is a column-based structure. So you basically construct it from columns rather than from rows. So when you want to append a new row to a column, this takes considerable time. And so you might think, what is the advantage of using this kind of data frame based approach? In fact, the main advantage is that when you have more complex problems. For example, here we want to combine the data with a data which we have stored in a CSV file on a disk, but it could be also from a database or other sources. And then you want to join it with our original data frame to know how many items you still have to produce. So in the orders, you have how many items you need to produce, and you join it. Then you group by the type of item, here by the color, and you basically calculate the difference to know how many left are there to produce. So this is actually becomes kind of very easy to do in polars in this case. And you could another thing is that you construct the data frame lazily. So all of this is not executed immediately. You only kind of start to construct the query plan, which is optimized, executed only at the end. So this is the query plan that you might see. And the advantage of using a query plan is that you can, for example, eliminate from the kind of query some data which you know that will be later discarded.
Yeah, sorry, can you slowly come to an end? Thanks.
That's the last slide. So thanks a lot for listening. So I just wanted to show you that you can use database-like solutions to simplify your analytical tasks. This is kind of consistent with data-driven design principles, which was a topic of talk by Srinat yesterday. Also, I see some similarities to ECS in Bevy, but kind of we can discuss this more. And it provides speedups thanks to the lazy processing and efficient I/O, column-based storage, and query planner, which can be optimized. But also there's some drawbacks such as overhead for the memory processing, loss of static type checking, and less reliability and less readable code. Thanks a lot.
Thanks so much for this fascinating talk. I have a question here from Miguel in the Q&A. So does Polars provide any facilities for intern strings or pool strings, i.e. intern strings not heap allocated, and pool strings are when you can store an integer instead of the different strings?
Can't tell you. I can't tell you. I don't really check this. So I don't know. I don't know. Sorry.
Okay. Okay. Then another question from myself, a quick one. So can you briefly explain, maybe we can discuss this later more, how you see the inspiration or similarities to entity component systems?
Yeah, it's basically that your units are basically not anymore like structures, but they have more like columns. So you have properties that you query to try them to get them to get the component to get data from. I mean, it's very loose. I find it's kind of loose, maybe comparison, but it's. I see that it's kind of the way it's organized. It lets you to be more, in a way, flexible in how you construct the units or your units and how you analyze them.
Okay.